Welcome to this lecture on advanced electric drives. In the last lecture, we have just started the vector control of induction motor, which is also called the field oriented control or transvector control. This is a advanced control technique for induction motor in which we can control the torque with high dynamic response. So today we will start with the vector control of induction motor. Now, by vector we mean there has to be an amplitude and a phase angle. Now, when we are controlling an induction motor, we are controlling the stator MMF both in amplitude and phase angle. So, when you are controlling the stator MMF with amplitude and phase angle, we call that to be vector control. The primary objective of vector control is to control an induction motor similar to that of a separately excited DC motor. There has to be a control similar to separately excited DC motor because in a DC motor we have separate brass, armature and field. So, let us see the structure of a DC motor. So, this is a DC motor we have the brushes here, this is the armature, and we also have a field winding. This is the armature of the DC motor. And often what we have in case of large DC motor, we also have a compensating winding. The purpose of the compensating winding is to neutralize the effect of armature reaction. And the compensating winding is connected in series with the armature, and the MMF of the compensating winding is in opposition to the armature MMF, so that there is a cancellation of the armature MMF and the effect on the field is reduced. So, we can also have a compensating winding here. And how do we connect it? We connect it in the following fashion. So, we have the armature current, we can say this to be IA, and we have the field current which we can say to be IF, and we know that the torque is equal to K into IA into IF, ignoring magnetic saturation. So, the objective of vector control is to control an induction motor just like a DC motor. So, the objective in this case, control of induction motor just like a separately excited fully compensated DC motor. And we have the flexibility in this case, we can control the torque by either controlling IF and IA, but controlling IF will be accompanied by a delay. So, we do not control IF, we keep IF constant and we control IA to control the torque of the DC motor. Similarly, in case of an induction motor, although apparently we do not have any field and armature, we have to identify a field current or a flux component of current and an armature current or a torque component of current, so that we can control this independently. We can control the flux independently and we can control the torque independently by some other component of current. So, this concept of field orientation or vector control was given by a scientist called Felix Blasquet way back in 1969. And that time he introduced the concept of field orientation, but it was difficult to implement the field orientation for some time because of non-availability of fast digital signal processing devices. We have to have faster computer to process the signals in real time to be able to control an induction motor just like a DC motor. So let's try to see the concept behind the vector control of induction motor. We can call this to be also field oriented control, or transvector control, or decoupled control. Now, if we take a 3-phase induction machine, we have 3 phases, phase A, phase B, and phase C. We can draw the 3 phases of the machine. This is the rotor, and we can have one phase here. We can have the second phase here, and we can have the third phase here. And similarly, the rotor can also have 3 different phases, phase A, phase B, and phase C. So these are the stator phases, and these are the rotor phases. And rotor is rotating. This is the rotor axis. And the rotor is rotating at a speed of omega r radian per second. And the stator is stationary, and this angle is the rotor angle, that is theta r. So what we do here, that we are talking about a 3-phase symmetrical induction machine. The rotor is rotating at a speed of omega r. We analyze the machine from a synchronously rotating reference frame, and the reference frame is so chosen that the reference frame is attached to the rotor flux vector. That is extremely important, that we are talking about a reference frame which is attached with the rotor flux vector. So we can say, for example, we can say this is the rotor flux vector, and this we can say to be psi r, which is also rotating. And the rotor flux vector is basically a flux vector that is rotating in the space with synchronous speed, and the synchronous speed is omega e. So this is the synchronous speed with which the rotor flux vector psi r is rotating. It's a vector having amplitude and phase angle. And when this is rotating, the angle between the flux vector and the stationary phase A axis, this angle is theta e. So what we do, we take a reference frame, and the reference frame is attached with the rotor flux vector. So we will choose a d axis. So this is our d axis. And we can also choose a q axis orthogonal to d axis. So this is our q axis. And this dq axis are rotating with the rotor flux vector at synchronous speed. And synchronous speed is omega e, and since this is a very special reference frame, we call this reference frame to be dE and QE, D superscript E and Q superscript E, symbolizing that these are the reference frame attached with the rotor flux vector. And when we are analyzing this from a rotating reference frame, we can always have fictitious windings like DES winding and QES winding. So we can have the stator windings which are fictitious. So we can have the windings here in the stator, and this you can call to be DS winding, but this is rotating with the rotor flux vector. So, we can call this to be ds superscript E. And similarly, we can have a QS winding, and the QS winding is also a rotating winding. We can call QSE. And similarly, in the rotor, we can always have an equivalent rotor winding also, like DRE and QRE. So, we can have a rotor winding here in the rotor. This is DRE, and similarly, we can have QRE. As we have seen in case of a Cron's primitive machine model, we can have two windings in the stator and two windings in the rotor, but these windings are not stationary, they are rotating at the speed of rotor flux vector, because the reference frame is attached with the rotor flux vector. Now, this is a very special reference frame. Now, if we are taking this reference frame, what is the advantage? The advantage is this, that if we are orienting the d axis of the reference frame, this is the reference frame d axis, along with the rotor flux vector, that is psi r, we have this following equation. The equation is this, that psi d r E is equal to psi r. You can see that if I find out the d axis component of the rotor flux, the total rotor flux is oriented along the d axis. So, we can say that the d axis flux is entirely psi r. And if I ask this question, what is psi q r E? What is the component of rotor flux vector or the rotor flux along the q axis rotor? And that will be equal to 0, because the rotor flux is entirely along the d axis. There is no component of the rotor flux along the q axis. So, we can always say that psi q r E equal to 0. So, this is very similar to that of a DC machine. Now, if you take a DC machine, in this case, that we have the flux along the d axis. This is our d axis. So, this is our d axis. So, we can call this to be the d axis here, and this is the q axis. And we can always say that the total flux is along the field. This is the flux produced by the field winding. What about the q axis flux? The q axis flux is 0, because in the q axis we have the armature winding, no doubt. We also have a compensating winding, and the compensating winding is compensating for the armature flux. It is cancelling the armature flux, and we are talking about a fully compensated DC motor, and due to this, the q axis flux in the rotor is 0. So, we can say that there is no q axis flux. So, in this case, the q axis flux does not exist. So, we are trying to have an analogy between an induction machine and DC machine in a rotating reference frame, and the reference frame is rotating at synchronous speed. And if the reference frame is rotating at synchronous speed, all the AC variables will appear as DC variables. Actually, if you see the phase A, phase B and phase C of an induction machine, the currents are AC currents, but these AC currents will appear as DC currents if we view them from a synchronously rotating reference frame. We can take an example. Suppose two trains are moving at the same speed. Okay? If the two vehicles are moving at the same speed, both the vehicles are moving, and a person is seated in one of the vehicles, he will observe the other vehicles to be stationary. Although both the vehicles are moving, the relative velocity between the two is equal to 0. So, if we are having a moving observer moving at the same speed, the speed of the other vehicle from the moving observer will appear to be equal to 0. Similarly, if we are housed in a reference frame rotating synchronously, the variables seen from the reference frame will appear to be DC variables, because there is no relative velocity between the reference frame and the AC quantities in the steady state. So, if we try to see that this is our currents, this is IDS E in the D axis, and this is IQS E in the Q axis, and similarly we can have IDR E in the d axis rotor, and we can have IQ or E in the q axis rotor, and these currents will be DC currents in the steady state. So, since the currents are DC currents, we can think of a DC machine. We can visualize a DC machine in place of an induction machine. So, to be able to control, we have to derive some equations, and the equations will give us the control scheme for vector control. So, what we will be doing in this case, we will be writing down the equations for d axis rotor. So, we are writing down the equation for the d axis rotor. So, we can say that VDR in the rotating reference frame, that is superscript E, that is 0, because the rotor is short circuited. That is equal to RR IDR plus P psi dr, and if you see in this case, the relative velocity between the reference frame and the rotor is omega E minus omega R. The reference frame is rotating at a speed of omega E, and the rotor is rotating at a speed of omega R, and the differential speed between them is omega E minus omega R, and we call this speed to be the slip speed. So, that is written as omega SL, and omega SL is called the slip speed. So, when we are writing down the equation of the rotor, the actual windings are rotating at omega R, physical rotor is moving at a speed of omega R, but the hypothetical winding in the rotating reference frame, they are moving at a speed of omega E. The relative velocity between these two is omega E minus omega R, and that is the speed at which the rotationally induced EMF will appear in the rotor equations. So, we can go back to our equation here. So, we have minus of omega SL into psi QRE. So, this is the first equation which is in the d axis. Now, we have already seen that psi QRE is equal to 0. So, we can cancel this. This is equal to 0. So, if psi QRE is equal to 0, we will again simplify this. We can say that 0 is equal to RR IDR plus P psi dr. Now, when we are writing down all these equations, all the variables are referred from the primary side. So, although we do not show in terms of primed variable, we assume that all the variables are observed from the stator. So, the effective number of turns have been multiplied. The parameters are also seen from the primary side. So, these equations are all written from the primary side. So, this is what we have here, and if we see in this case that psi dr equal to psi r, and we would like to keep the flux constant, because if we change the flux is associated with some inductance, and the flux cannot be changed instantaneously. It will take some time for the flux to change. So, if we change the flux, the torque response will be delayed, and to change the torque, what we do, we keep the flux constant. So, what we say here that psi r is kept constant, or the rotor flux is kept constant. So, if psi r is kept constant or psi dr is kept constant, we can say here that P psi dr equal to 0. And from this equation, what we obtain here is that RR IDR equal to 0, or IDR is equal to 0. So, it means there is no d axis rotor current. So, as if the d axis rotor winding is absent, or that winding is not having any effect on the machine performance. So, this is the first equation of the vector control, that in the d axis we have IDR equal to 0. So, this we can say as number 1. So, similarly in the q axis, rotor, we can write down the equation for q axis rotor. VQRE, that is short circuited, so that's equal to 0, and that is RR IQR plus P psi QR plus omega SL psi dr. We are again writing down this equation in the rotor flux reference frame, and the reference frame is rotating at synchronous speed, and the speed of the reference frame is omega E, and that is why the speed induced EMF is appearing with a factor of omega SL. Omega SL is the slip speed. Now in this case, this is equal to 0 because we don't have any q axis flux. Psi QR is 0 here, and because of this, this quantity will vanish. So we can say in this case 0 is equal to RR IQR plus omega SL psi dr, and we can find out the value of omega SL here. Omega SL is equal to minus of RR IQRE by psi dr. So this is the expression for the slip speed. Now the slip speed expression is quite interesting. The slip speed is proportional to IQRE, and it is inversely proportional to psi dre. Now we can substitute for IQRE because IQRE is the rotor current in the q axis, and the rotor currents are not easily accessible. So we have to replace the rotor currents by stator currents. So we can say here that psi QRE equal to 0, and that's equal to LR IQR plus LM IQS, or we can say here that IQRE is equal to minus of LM by LR IQAC. So what we will do here, we will substitute for IQRE in this case. So we can rewrite this equation for the slip speed. That's equal to RR by LR into LM IQAC by psi dre. LR by RR is called the inverse of the time constant. So we can say in this case it is LM by tau R into IQAC by psi dre. So the slip speed expression will be useful when we control the induction motor with vector control. Now here we can also have another simplification. We know that psi dre is equal to, as we wrote the expression for psi QRE, similarly we can write for psi dre. Psi dre is LR IDR plus LM into IDS. And we have already seen that IDR equal to 0. This is what we have already seen. So we can substitute this IDR equal to 0 in this expression. So this will be 0. So this vanishes in this case. So what we have here is that psi dre is equal to LM into IDAC. Now it means the rotor flux can be controlled only by stator current. If we vary IDAC, we can change the rotor flux, and psi dre is same as the total rotor flux, that is psi r. So when we change IDAC, we can change the rotor flux. And in the expression for the slip speed, we can replace psi dre by LM into IDAC. So we can write the expression for the slip speed, and the slip speed here is 1 by tau r into IQAC by IDAC. So this expression for the slip speed will be useful for us when we control the induction motor with vector control. Now let us see how it will be useful. So we have been able to find out the slip speed and the other equations. Now what about the torque? Torque equation is given us for an induction motor. We know it is 3 by 2 into P by 2 into Lm into IQS IDR minus IDS IQR. And since we are talking about a rotor flux reference frame, we'll have to put a subscript here. So this is the torque equation of an induction motor. And we can further simplify this, and this, if we simplify this, what we will do here, we will replace this IDR by psi dr minus, we can say here Lm into IDS by Lr, and similarly we can substitute for IQR. IQR is psi QR minus Lm IQS by Lr. So if we substitute for this IDR and IQR, we can get back the torque expression in a different form. So we can rewrite the expression for the torque 3 by 2 into P by 2, and after simplification we will get Lm by Lr into IQS into psi dr minus IDS into psi QR. So these are the expression, this is the expression for the torque of an induction motor as a function of the stator currents and the rotor flux. And this equation will give us the equation of the torque as we have seen in case of a DC machine. So what we have here is the following, that we have psi QR equal to 0. Now if psi QR is equal to 0, we can make this equal to 0, and if psi QR is equal to 0, we can rewrite the expression for the torque as 3 by 2 into P by 2 into Lm by Lr into IQS into psi dr. And this is a simple equation compared to a very complex equation of an induction motor, and the torque can be produced by the product of two variables, and one is the flux and other is a component of stator current. So this is called the torque component of current. And this is the flux, so we can rewrite this expression for the torque as 3 by 2 into P by 2 Lm by Lr IQAC, and we can substitute for psi dr, and psi dr is Lm into IDAC. So that will give us the following expression 3 by 2 P by 2 Lm square by Lr into IQAC into IDAC. So we see that the equation of the torque for an induction machine is just like a DC machine. If you see the DC machine torque equation, what we have is that T is equal to K into IA into IF. And what we have here is something very similar. We have, in case of an induction machine that we have just seen, it is 3 by 2 into P by 2 into Lm square by Lr into IQSE into IDAC. So this IQAC is comparable to IA. So we can say that this is something similar to IA, and IDAC is something similar to the field winding current. So we have two types of current here, two components of current, that is IQAC and IDAC. IQAC is called, as we have already seen, this is called the torque component of current, and IDAC is called the flux component of current. So we have two, that is IQAC, the flux component of current, that is IDAC. So if we control these two currents, we can control the torque of an induction machine just like a DC machine. So usually what we do here is the following: we keep IDAC constant. So this we can keep constant, because if we change IDAC, the flux will change, and if the flux changes, there will be a delay. So we keep IDAC constant and we change IQAC for the torque control. So the torque is controlled not by IDAC, primarily by controlling IQAC, because when we control IQAC, there is no delay involved. So IQAC can be controlled quickly and the torque will respond linearly to IQAC. Now let us see the control scheme. Control scheme for this is called rotor flux oriented vector control. This is called rotor flux oriented vector control because the reference frame is oriented along the rotor flux, and hence it is called a rotor flux oriented vector control. Now we have two currents in this case, IDAC and IQAC, but this IDAC and IQAC are hypothetical currents. They are the currents in a rotating reference frame which is non-existent, and this is only in our mind. This is only in the concept. Now when we are actually controlling the machine, we have to translate or we have to transform this IDAC and IQAC into the actual currents of the machine, and the actual currents are IA, IB and IC. So we have to transform this IDS and IQS into IA, IB, IC. So what we have to have here is the following: we have to have a transformation. So this is our IQAC and this is IDAC, and we have to transform these two current components into the actual currents of the machine, and that is IA, IB, IC. Let us see our original diagram here. Actual currents in the machines are IA, and this is phase B, IB, and this is phase C and IC. And we have been able to evaluate what is IDAC and what is IQAC. These currents we know, but these currents are hypothetical currents. Although we can do the control in IDAC and IQAC, we have to actually inject IA, IB, IC into the machine windings. So we have to transform this IDAC and IQAC into IA, IB and IC, and thus it involves a transformation. And if we see that this reference frame is having an angle of theta E with phase A, so the transformation will involve theta E. So the transformation that is applicable here is a transformation that will involve theta E. So we can say here that if you want to get back IA, IB, IC, we have to use a transformation as follows. So the transformation in this case is IA, IB and IC. This we have to obtain from IDS and IQS. And what is the transformation here? This transformation we have to find out. The transformation will involve theta E. Now the transformation will be as follows. This will be cos theta E. This is cos theta E1. This is cos theta E2. This is minus of sin theta E, minus of sin theta E1, minus of sin theta E2, and where theta E1 is equal to theta E minus of 2 pi by 3, and theta E2 is equal to theta E plus 2 pi by 3. So, this is a transformation that will transform IDS and IQS into IA, IB, IC. And when we obtain this IA, IB, IC, we can use an inverter to inject this current to the windings of the actual machine. So, in fact, these currents are the reference currents. So, we can say here IA star, IB star and IC star, they are not the actual current, they are the reference currents. So, they have to be impressed onto the machine windings. Similarly, these currents are also IQS star and IDS star. So, we can have an inverter to inject these currents onto the machine winding. And this transformation, as we are seeing, this will involve theta E. And what is this theta E? Theta E is the angle of the rotor flux vector. If we see, as we have already drawn here, this angle is theta E. Now, as you have already seen that we need theta E for the transformation from IDS, IQS to IA, IB, IC. Now, there are ways to evaluate theta E. Theta E can be evaluated indirectly, it can also be evaluated directly, and accordingly we can have an indirect vector control or a direct vector control. Evaluation of rotor flux vector angle theta E. So, we know that theta E is obtained by integration of omega E. Omega is the speed of the reference frame, and this is also the speed of the rotor flux vector. Now, if we integrate this omega E, we get the angle that is theta E. That is one way. And how do you find out this omega E? Omega E can be evaluated as omega R plus omega SL. So, if we add the rotor speed and the slip speed, we get the synchronous speed, that is omega E. Now, slip speed can be calculated. We have already seen that slip speed is given by 1 by tau R into IQS by IDS. So, if we know IQS and IDS, and if we know tau R, and tau R is the rotor time constant, that is equal to LR by RR, we can evaluate what is the slip speed, that is omega SL. So, slip speed can be easily calculated, and the rotor speed, that is omega R, can be measured by using a speed sensor or an encoder. So, we can measure the rotor speed, we can calculate the slip speed, and then the summation of these two will give us the speed of the rotor flux vector, that is omega E. Integration of that will give us theta E, and theta E can be used to transform IDS and IQS into IA, IB and IC. Now, this is called indirect vector control. As theta E is evaluated indirectly. This is one of the ways to evaluate theta E. Now, the second method of evaluating theta E is to sense the rotor flux. If we can sense the rotor flux in the D axis and in the Q axis, stationary D axis and Q axis. Suppose we are having a machine. These are the machine windings, the stator, AS, BS and CS, and this is the rotor, and we want the rotor flux vector. So, we can have some sensor in the rotor, and this is our stationary D axis, and this is the stationary Q axis. So, we can find out what is psi dr, and we can find out what is psi qr in the stationary. So, psi dr and psi qr can give us theta E. So, we can say that theta E is obtained by taking the tan inverse of psi QR and psi dr. These are the stationary flux components. Psi dr and psi QR are the stationary flux components. Now, if we have a rotating flux, the actual flux is rotating at omega e, and this flux will have two components. One is psi dr, this we can call to be psi dr, and this can also have a component in the q axis, that is psi QR. And the angle in this case is theta e. Now, if we want to evaluate the angle, we have a right angle triangle and the perpendicular is psi QR and the base is psi dr. We can evaluate the angle theta e as tan inverse of psi QR by psi dr. This is pretty straightforward. But the difficulty in this case is that how to sense the rotor flux. The sensing of the rotor flux is not very easy, because rotor is a moving member and housing the sensor inside the rotor is very difficult, and this cannot be used for retrofit application, and hence we cannot have rotor flux sensors inside the rotor. So, if we do not have rotor flux sensor, how to sense the rotor flux, how to evaluate the rotor flux? That can be evaluated by using flux estimator. So, what we can do is that we can estimate psi dr and psi QR, and the estimation of psi dr and psi QR can give us psi dr hat and psi QR hat, and then we can evaluate what is theta e from the estimate. These are the estimates, and from the estimates we can calculate or we can evaluate what is the rotor flux angle, that is theta e. So, this is called direct vector control. Because in this case we are able to find out theta e directly without taking the help of slip speed. So, we will now see a control block diagram of a vector control drive. So, we have here the transformation block, and this angle is theta e, which is used for the transformation. We have the reference speed in this case omega r star, then we are subtracting the actual speed, we are feeding it to a PI controller, then we can as well have a limiter in this case, and the limiter is used to limit the output of the PI controller. In case we do not have any limiter, sometimes the PI controller output can reach a very large value. So, to limit to the practical value, we have to have a limiter after the PI controller, and the output of the limiter is the reference torque PE star, and this we can divide by 3 by 2 P by 2 Lm square by Lr into IDAC. So, what we obtain here is IQAC. So, this is what we can divide here. This is the numerator and this one is the denominator, and this is IQAC star because this is the reference torque component of current, and IDAC is given directly. What we have here is IDAC star because we want to keep the flux constant and we are keeping IDAC constant. So, this IDAC star is fed directly, we are not changing IDAC, and from IDAC and IQAC we can evaluate the slip speed. The slip speed is 1 upon tau r into IQAC by IDAC omega SL, and we have the feedback from the two currents. And then to the slip speed we are adding the rotor speed. And what we obtain here is omega E. Omega SL plus omega R is equal to omega E, and that when we integrate this, we get theta E. So the integration of omega E is theta E, and this theta E will transform IDAC star and IQAC star into the three stator currents, IA star, IB star and IC star. And then we have the comparators here. We can have the current comparators, and this we can have some sort of controller. For three independent phases, this is for phase A, this for phase B, this for phase C. Here is our inverter. We have a DC input of the inverter, and this is an inverter, maybe having IGBTs or MOSFET, and then we have the induction motor here. The inverter will have the three-phase output, and outputs are fed to the induction motor, and we have a speed sensor or a tacho generator here. The tacho generator will be giving the output, and then this is omega R. This will be giving us a mechanical output. So what we can do here is that we can multiply this by 2 by P or P by 2. So this is P by 2. This will be omega Rm, the mechanical speed. And then we can multiply by P by 2 to get the electrical speed. And the electrical speed is fed back here. And this, what we are controlling, is the electrical speed, which can always be scaled. So this omega R here is the electrical speed, omega Rm is the mechanical speed, and hence we have to multiply the mechanical speed by pole pair to obtain the electrical speed. So this is the closed loop control, and this will be giving the gate drive signal for the inverter. So these are the gate drive signal. And this feedbacks will be IA. This is the actual current that is fed back. Here we have IB, and here we have IC. And in this case, we have three different phases. This is A, this is B, and this is C. And the currents here are IA, this is IB, and this one is IC. So we can have the current sensors. We can have the current sensors in 3 phases to give us IA, IB, and also for phase C we can have another current sensor to give us these 3 signals. Okay? And these 3 signals can be fed back as the feedback signal for phase A, phase B, and phase C inverter control. So this actually is a closed loop control block diagram for indirect vector control. It is called indirect vector control because the sweep speed is calculated and we are adding the sweep speed with the rotor speed to evaluate the transformation angle, that is theta. Now we will focus on the control of the inverter. This is the inverter. This inverter is a voltage source inverter. So let's try to see what is the structure of this inverter. So if you see the structure of the inverter, this inverter would be a 3-phase inverter. Something like this. And this is the DC voltage, and these are the 3 switches of the 3 phases of the inverter. We have, say for example, phase A, phase B, and phase C. And since this is a VSI, the transistors will have an anti-parallel diode. So we have the diodes here to facilitate bidirectional flow of current. So this is a voltage source inverter. And the currents are in this case IA, IB, and IC, and these will be feeding to the motor. So we have phase A, phase B, and phase C of the machine. So the inverter feeds to the induction motor. And we have the inverter switches. We can call this to be S1, this to be S3, this to be S5, this to be S4, this to be S6, and this to be S2. So we have 6 switches, and when we have 6 switches, we have to have 6 gate drives. So the 6 gate drives can be fed to the transistor 1, S1, S2, S3, S4, S5, and S6. The objective is this, that whenever we have a phase A current, the actual current should follow the phase A reference current as faithfully as possible. So in this case, what we have here is the following. We have phase A current. This is IA star, and the actual current will follow the reference current within a band. So this is how the actual current will look like. This is IA. So what we do, we have a reference current that is IA star. We define a band around the reference current. We have upper band and we have a lower band. So this is the upper band called IA star plus H. Star means the reference current. Similarly, we have a lower band which is shown as a dotted line. So we can call this to be IA star minus H. So what we are trying to do here, the actual current is made to follow the reference current within an upper band and a lower band, and this is called hysteresis current control. So we can call this to be hysteresis current control. So, if you talk about a particular phase, say for example phase A, if we want to increase the phase A current, we switch on the upper switch, and if we want to decrease the phase A current, we switch on the lower switch, and we go on doing like that, and hence the current will rise and fall, rise and fall. So it will basically follow the actual current, I mean the reference current within the band. So this has got other name also. We call this as bang control. So we have to control the inverter in such a way that actual current will follow the reference current within the hysteresis band. So this is for phase A, and similarly we can control phase B and phase C current, and phase B is shifted from phase A by 120, phase C is shifted from phase B by 120, and the inverter is controlled in such a way that the inverter will inject the actual current within a hysteresis band of the reference current onto the three phases of the machine, that is phase A, phase B and phase C. The currents are controlled using hysteresis current control technique, by proper switching of the inverter switches. So we can just have a logic that if IA is higher than IA star plus H, S1 is turned off and S4 is turned on. And if IA is less than IA star minus H, S1 is turned on and S4 is turned off. So this means VDC is equal to 0, or V, the voltage here will be equal to 0. So it means we have VAN is equal to 0, and this means VAN equal to VDC. Now, if we see this inverter structure, we can define a P and we can define an N here, and these are our three phases A, B and C. So we are concentrating on phase A. Now if you concentrate on phase A, we can define VAN, VA capital N. Now if the current is hitting the upper band, it means it is increasing. So we have to bring it down. Now we have to bring it down by switching the lower switch. The lower switch is S4. So in this case, if it is hitting the upper band greater or equal to this, we can switch off the upper switch and switch on the lower switch. It means we can make VAN equal to 0. And if IA is lesser equal to IA star minus H, it means the current is hitting the lower band. We have to switch on the upper switch. We have to increase the current, and the current can be increased by switching on the upper switch and switching on the lower switch. So that's what we can do here, that if IA is less than IA star minus H, we can switch on the upper switch and switch off the lower switch. And S1 and S4 are complementary. We can see this inverter structure that these two switches are complementary. The gate drive to S1 is the inverse of gate drive to S4. Similarly, the gate drive of S3 is the inverse of gate drive of S6, and gate drive of S5 is the complement of gate drive to S2. So these are complementary switches, and this is basically the structure for one phase, that is phase A, and we can similarly have for phase B and phase C, and hence we can control the three phases as per the reference current requirement, and when we control the three phase current, the machine is automatically controlled under vector control. So in this particular lecture, we have discussed the vector control of induction motor. We have seen how the vector control is similar to that of a DC motor control. We have derived the expression for the slip speed. We have seen what is the difference between direct vector control and indirect vector control. We have also seen a control block diagram of closed loop speed control of induction motor with vector control. So in the next lecture, we will try to see that instead of keeping the flux constant, if we vary the flux, how does the response change? So we will see the vector control operation under variable rotor flux.